third class, the same lecture. I think benefit was it's important that we understand standard mass mechanisms very well first before we go to exotic ones. Yeah. This is not on the web page. Oh, okay. So, okay, I try again. There was some confusion. Maybe.
So sterile neutrino is supposed to be unless sterile neutrino is
you've just written sterile neutrino.
So at some point the title was wrong.
Yeah. That's the
Since it has been almost a week, we into the last. So let me just try to remind you of what we were doing. So first thing we were doing is trying to look at standard model Lagrangian in steps. So this I'm going to go extremely quickly, as in 5 seconds per slide. So if I really wanted to get a Lagrangian, I'm starting first with only particles, no interactions. Then we added U1 base theory, and that gave us these red terms. Then we added our SU2L. SU2L gave us these red terms. So now we have the gauge part of that. Okay. So this part of Lagrangian was something that was forced on us. As soon as I tell you that my Lagrangian is SU2L cross U1Y, okay, I cannot escape this. So this is compulsory. I don't even have a choice. Not even a state issues. This is just cancelled. Okay. And the next thing we are going to talk about is how to get massless solutions. Because this Lagrangian, which was forced on us, actually did not have any masses. This the fermions are massless, the Higgs bosons are massless. Actually, the Higgs has a mass. This V phi that you see here, okay, can have a mass. We'll come to that. But at least the fermions and Higgs bosons don't have masses. Before we go further, there was some confusion about normalization in the last class. Can you clear that up? So we were trying to see what this term looks like. The interaction term between the left-handed doublet, W, and left-handed doublet. So if we look at this, Lagrangian, this red term is N bar, gamma mu, W dot tau times N. Now we saw last time that this term you can expand it by writing N bar as V bar E bar, N as E, and W dot tau is essentially there are two vectors. So W1 tau 1 plus W2 tau 2 plus W3 tau 3. Tau are sigma matrices, Pauli matrices. So if I expand that into something like this, then I wanted to write this thing down in another sort of simpler format or useful format. So I write it down as W1 times tau 1, W2 tau 2, W3 times tau 3. So this gives me off-diagonal terms of W1 minus IW2 here, W1 plus IW2 here, and W3 minus W3 on diagonal. This term is fine. This term is simply W3 times tau 3 as it was. Now, this term, I define W plus as W1 minus IW2 over root 2. So we get W plus equals W1 minus IW2 and W minus equal to W1 plus. So once I do that, the first term is written as root 2 times W plus and W minus. Okay. Now I gave you a definition of tau plus as tau 1 plus I tau 2 by root 2, okay, which was not. Standard definition is tau 1 plus I tau 2 by 2. So this should actually be 2.
Okay. That is the normalization for Pauli.
Yeah. So this means that my tau 1 plus tau 2 by 2 will not have this root. So So my tau plus is simply 0, 0, 1, 0, which is raising operator without any organization. So therefore, these two terms will have a root 2 factor. Times w plus tau plus minus tau minus plus. So that's where the root 2. So then if I want to go ahead and want to write down what this looks like, these two terms will have a root 2 factor. This will have a root 2. This will have a root 2. So w plus tau plus. And therefore this first term therefore will have multiplication of the root 2. And this term will have multiplication. These two get multiplied. This third one stays the same. So again this is root 2. This is root 2. This is root 2. This is root 2. And which means that if I write this vertex, which is vector neutrino W, I get a G by root 2. So, and if I get the standard normalization, this is also G by 2. And this is as G by 2 because okay. So this is when time came to connect the vertices of W plus W minus and W3, this problem was enough. So this is standard normalization. We have G by root 2 here, G by root 2 here, and G by 2. So this was just okay. So now let's try looking at the mass of the sun.
So this leads to the extra factor of 4 in the neutral current X square. There is a difference of 4. This is a
I cannot connect.
if you write GF, if you take GF and then you write the neutral current term plus the charge current, there is a factor 4 which is here, which is probably because this is 1 by 2. So you take two vertices 2 and then take the matrix square that is because of this.
Perhaps, but I cannot guarantee at this point because I don't have that in front of my eyes. So this is normalization. So then you do whatever you want to do. Okay, so let's start to see how to give masses to these particles. So before giving masses to the particles, okay, the masses have to come through interactions. Let's first see what are the interactions that are possible. So this was the table that we also saw the last time. I have changed the notation to make it conform to the standard one. So QL is the left-handed doublet of quarks, which is ULTM. And then it is 2 1/3, which means there is doublet under SU2 and Y is equal to 1/3. Then UR and DR are the right-handed up and down quarks. Both of them are singlets under SU2 and Y values are 4/3 and -2. This is given to us. Standard model is constructed, these values are given to us. The electron doublet I call as LL, and that stands for neutrino and electron. Left-handed. This is again doublet under SU2 and Y is equal to -2. Again something that's clear. We have right-handed electron, which is singlet and Y is equal to -2. And we do not have nu R. It's historical in some sense, but also it has some other implications. We will see it in tomorrow's class. But as the standard model stands, there is no nu R, only ER. Therefore, this part is. Then we have Higgs, which is a doublet, 5+ and 5-0, which is doublet clearly under SU2. And Y is equal to 1. Higgs were given these charges, so doublet and Y is equal to 1, by Feinberg and Salam. It turns out that this is the simplest Higgs that works with experiments and also for the electroweak symmetry breaking mechanism. turns out that, so this was a guess of Weinberg-Salam, and it worked very well. And therefore, now we call the Weinberg-Salam model as the standard model. But this is to be remembered that this was just a guess that mode. Nothing told you that it has to be of this kind. This was just happened to be a connected mode. I will come to what the test for this model.
So, standard model, there is no trace of right-handed neutrino. So,
standard model does not have right-handed neutrino. Okay. If you add to it, it becomes beyond standard model in some sense. Okay. So tomorrow we will talk. So adding this new R, okay, is not just as simple as adding ER. Because if you add new R, many more things happen. But that will come to tomorrow. So right now, the way standard model is written, we don't have a new. Okay. So our standard Higgs is this 2-1 particle, which is 5 plus and 5 0. Turns out that given only this particle, we can also add another field, which is called as the conjugate field. Okay, it's the conjugate particle of a scalar doublet. That's usually written like this. Now, this strange thing that you see I tau 2 times phi star is done so that you still get a particle which is doublet of SU2. So this is property of SU2 again. So if you haven't done much of SU2 algebra, perhaps you don't know why this comes about. I have to just take it from me that once we have phi, we also have this. You can call this as the charge conjugate of phi, okay, or phi c, phi conjugate. Phi conjugate. So this is phi plus and phi 0. Phi conjugate is phi 0 star and minus of phi minus. And this part, all these signs and stars are done so that SU2L is preserved. So right now, let's just take that for an example. So this state is doublet of SU2 and y is equal to minus. Okay, so y had changed. So clearly it's a complex conjugate particle, and therefore the charge conjugate particle, therefore y is equal to 1, y is equal to minus 1. Okay. If you are written in any other form, if I have just written this as phi 0, phi minus, it would not be SU2 doublet. For it to be SU2 doublet, I need it to have this star and this minus sign. So therefore, now we have got all these fields. The question now is, with all these fields, which are the Lagrangian terms that we can write? What does that mean? Lagrangian terms we can write. It means that this term should be invariant under SU2 and invariant under U1. There are of course other things. It should be always invariant, but that automatically happens. And we have restricted ourselves to non-observable theories, which means that the dimension should be at the most 4. So which means we cannot have long sequence of these terms. We can have only 2, 3 or 4. Fermions are dimension 3 by 2, so you can't even have 4. If you want to have fermion like Q and U, you can only have 3 terms. So we should conserve first U1y, which means that if you take y1, y2 and y3, the y's of these 3 particles, you should get 0. Okay, that's one. So Lagrangian terms. So firstly, we should have y1 plus y2 plus y3 equal to 0. Secondly, all these SU2 should also give you 0, which means that you are in some sense, okay, tau 1 plus tau 2 plus tau 3 will be equal to 0. Okay. In concrete terms, what does this mean? This is like saying the sum of 3 spins is equal to 0. So this is like saying that if you have T, which is isospin, half or 0, so T1 and T1Z, the third component, Z component, and then you have got T2 plus T2Z plus, sorry, so T1, this is the state. Okay, it says this is the isospin and this is the Z component of isospin. Plus T2 and T2Z. These two sets of particles, okay, not one. And then we have got T3 and T3Z. This should be equal. So this tells you actually two things. So this is something akin to the Wigner-Eckhart theorem. Okay, what does Wigner-Eckhart theorem say? If the sum of these has to be equal to 0, then T3 must lie between.
Does it say that there will be one state which has total spin 0? This will say that this is the outer sum. So then you can break that into outer products.
Yes.
So this will say that there exists one singlet state over there.
Yeah. So this 0
Does it mean you can write it? I know what you're trying to say, but can you write this?
Well, I got around this by not using a plus sign, but a plus inside a circle. So what does this mean? This means that I add 3 spins and get a 0 state. So it firstly means that my T1, T2, and T3 should satisfy the triangle inequality. So since we only have spin half particles and spin 0 particles, only spin half and spin 0 particles, you have spin 1. It basically means if you have spin half and spin half, third thing can only be spin 1 or spin 0. Then another thing is that I must have T1Z plus T2Z plus T3Z is equal to 0. If I take third component, the third component of all these 3 must add to 0. So just like my Y in the scalar quantity which is concerned, this is also constant. It is like Jz. So if I have 3 spins adding up to 0, it means that Jz1 plus Jz2 plus Jz3 is 0. Okay. So these are the 3 conditions I have. Y, T, and the fact that T1, T2, and T3 can make spin 0 particle. So now we'll go through all these combinations and try to say which ones actually work. So of course there are lots of things that we can try, but it turns out that only a few of them work. So I'll tell you which are these, and then we'll see what. Okay. Firstly, we have, let's say we start with this. So L bar phi ER. So let's see what that means. So I say L bar phi. So what does this mean? LL was 2 minus 1. So 5 was what was 5? 1. So sorry, L is 2 minus 1. L is 2 minus 1. L is 2 plus 1. And ER is 1. So therefore we see that at least Y matches, okay. And doublet, so spin half, and spin 0. Right? Doublet single. So that is okay. Now let's expand it and then we'll see what it actually gives. So LL bar is this new L bar E bar. Phi is phi plus phi 0. ER is ER. So this is new L bar phi plus ER plus E bar phi 0, this is L. EL bar phi 0. So now, for each of these terms, if you want, you can check for conservation of Y, conservation of T3. Okay, we are sure that Y will be true because of this, right? So Y you already checked here. Before we expand, we cannot check for T3 because the expansion has all T3. So you cannot check for T3 conservation at this level. For T3 you have to expand. So these two are different. So let's see. T3 conservation. So what is the T3 of mu L bar? So mu L is plus half. So mu L bar is minus half. So this is minus half. 5 plus is 5 plus phi 0. So plus half. Okay. Plus half. And ER is single. So it's a 0. So this term is okay under T3. Here, EL bar is plus half. So EL is minus half. EL bar is plus half. Phi 0 is minus half because it's lower. So minus half. And ER is 0. So this term is therefore allowed. Okay. And this is invariant under SU2. So we can always write SU2 and both. Y of course we checked already. So Y, the mu L bar is just that, so it's just plus 1. Phi is plus 1, ER is minus 2, so that works. And again EL bar is plus 1, Phi is plus 1, ER is they have to be the same because after all the Y is the same for mu L bar and EL bar. So this is kind of double checking. So if you wrote things in the language of doublets, then you can check for addition of spins at Y. But if you expand it like this clearly, then you can check for T3, Y and addition of spins. So this is like adding two spin-off particles. If you add two spin-off particles, you will get spin 1 particle and a spin 0 particle. The spin 0 particle is here is what we got. So mu L bar. So this is another. Okay, don't take it too seriously, but it's enough for rule of thumb. So spin 0 particle here is what we wrote. EL bar. Sorry, mu L bar. Phi plus EL bar phi 0. Using these two, you can also write a spin 1 particle.
So, the particle was because mu L is a particle, mu L phi 0 is a particle or
mu L phi. It's a combination of two particles. So let's say we're talking not about particles but about states. I'm just counting the spins of these states. Okay. So it's like you take two electrons. What is combination of two electrons? The two electrons. So combination of two particles is a two particles. Okay, so I'm just trying to see what is the weak isospin of this. And for simplicity, I keep on calling it as spin. When I say spin, I actually mean weak isospin. It's also another combination. So you might, for example, get something like mu L bar phi plus. You can get EL bar phi 0, and then you can get mu L bar phi 0 minus EL bar phi plus pi root 2. So, given two isospin doublets, you can form one isospin singlet, which is this, and you can form one isospin triplet that looks like this. If you calculate T3 for this, you say T3 for nu L bar 5 plus S. Sorry, not 5, sorry. So this is -1. Then if you see EL bar 5 minus, EL bar 5 plus, 1. It is 1. And then I will have UL bar 5 plus, UL bar 5 0. Okay. And this will have T3 equal to 0. Okay. So this is T3 equal to plus 1, 0 and minus 1. This is a triplet. We don't want triplets. Okay. At least in today's class, we don't want triplets. We may want triplets maybe after one more, right? At this point, no. We only want singlets. Therefore, we take only this combination and gives the spin 0 1. Okay, this also has T3 equal to 0. Okay. Similarly, I can look at this term. So QL bar phi dr. So like that term. So QL bar phi dr basically means that I have UL bar UL bar DL bar phi plus phi 0 times dr, and this basically means I have UL bar phi plus dr plus DL bar phi 0. And we can check now that all the three conservation laws work. So y1 plus y2 plus y3 is 0 for all these three. Okay. Again, t1 plus t2 plus t3 is 0, and the spins actually match. Okay. The spins match is actually given. So if you can form a singlet out of this, it means spins match. Okay. Because only with spin half and spin half can you form a singlet. The third term that I had written down was UL bar phi conjugate times UR. So this is UL bar phi conjugate times UR. So this will be UL bar EL bar phi conjugate was phi star and minus of phi minus. This will be phi 0 UL bar phi 0 star bar minus DL bar phi minus. So note that when you add phi, you cannot have QL bar phi UR because UR has different value of phi.
What is that? Is the phi plus? The plus in phi plus stands for?
The charge scalar.
Charge is in hypercharge.
No, electric.
Electric. So phi minus means negative.
Minus negative. Okay, so I can take it as phi1, phi2 if you want. Because unless we do electric symmetry, we don't know what you charge.
Minus and this is phi star, phi complex conjugate. And then phi 0 star, and there should be phi plus star, not minus phi minus.
So phi plus star is phi minus. So this is
Minus phi plus.
phi plus star is phi minus.
There is a transformation between IT.
Okay. Okay. So phi conjugate we do it. So phi conjugate is I out2 times phi star. Okay. So let's see what happens. So phi conjugate was I out2 times phi star. So which is I. Out2 is means phi star is now phi plus star and phi 0 star. So this is 0 1 minus 1 0 times. Now phi plus star is defined as phi minus and phi 0 star is phi 0 star. So this will give me phi 0 star. So that's something. So there I can write term like this.
Why have you raised and told the index of the sign? Phi 0 is a subscript here.
Oh no, it's just a convention. It's nice. So you can choose whichever way you want. There are many conventions. So that's not very important. What's important here is that if you want to form a term with QL bar and DR, you must have phi. And if you want to form a term with QL bar and UR, you must have phi conjugate. Okay, and that's because the bar of UR and DR are very different. So therefore, if you want to form QL bar and UR, this is 1/3 and this is 4/3. You must have this and minus 1. Whereas if you want to form 1/3 and minus 2/3, then you must have this phi as well. So this is very important. That the phi will always only couple with DR and phi conjugate will only couple with UR. So the reason I am stressing on this is because if you look at the electronic term, phi couples with ER. In case you want to add a new R at some point of time, you should remember that this new R will not couple with phi. It will have to couple with phi conjugate. So in the isospin doublet, the lower part will couple with phi, the upper part will couple with phi conjugate. So this is not a choice, this is something forced on me. Once I said that I want terms which are SU2 and one invariant, this was forced. So note that till now we have got no masses. I mean, there was nothing that looked like a mass here. These are interaction terms. So this will mean that I have a UL coming in, I have a DR going out, and I have a phi plus. This means that I have a DL coming in, I have a DR going out, and I have a phi 0. Similarly, if I went to an electron part, this means a new L coming in, ER going out, and a phi plus. And this means that I have an EL coming in, ER going out. So interaction terms give us vertices, they don't give us masses.
Isn't the bar isn't the bar going up?
Both conventions exist. Both conventions exist. So yeah, so many books will say
So it won't matter, the final whatever can
everything won't matter. Because everything always is plus summation conjugate. Okay, so therefore it won't matter.
And after passing through vertex, is it necessary to change the elasticity? Algebraic or
This is your interaction term. See, I have no control over what to do with elasticity. Okay. My interaction term is given by this. See, my EL and ER are different particles. See, standard model, I don't try to say that I have electron which has a left component and a right component. I say I have two different particles. I have EL, I have ER. They are different particles. Okay, they have different eigenvalues. No? They have different Y values, for example. So I don't consider EL and ER as the same particle. No, they are different particles. And this is interaction term. So I am not allowed to change anything about L and R. They are just, you can look at them as two particles which have the same name, electron. Okay, but all those properties are different. So one is EL, one is ER. So these terms right now are just vertices, okay, no masses. So what do we need for masses? Okay, so when do we say something as a mass? So for that, let's go back a bit and let's see what it means by having a mass. So usually you have a Lagrangian. The theory is given by Lagrangian. once you are given a Lagrangian, then you write equations for motion. And that's basically like this. So you take Lagrangian, which is Lagrangian in some psi. This can be Fermion, boson, whatever you do, some field psi. Okay. Then you take derivative of A with respect to tan alpha of psi. And then take derivative of this. This should be equal to tan by tan psi. This is the Euler-Lagrange equation of motion. So even when you do classical mechanics a la Goldstein, this is exactly what you do. And you don't have psi there, you have x or q. Okay, but equation do exactly like this. So this is how you come to field theory. In field theory, instead of writing x, you write field psi. And then you understand things. Now, if I have a complex scalar field, then my Lagrangian, if my Lagrangian is like this, then mu phi dagger, then mu phi minus m square phi square. Then from that I write equation of motion, then I get this. And this you recognize as a Kyle-Gordon equation. So I think these three things I will give you in one of the assignments to actually go. So in fact, because you want to get this Kyle-Gordon equation, that's the reason why you put such terms in the Lagrange. Okay, so it actually works the other way around. You know that this is a scalar field, you should satisfy Kyle-Gordon equation, and therefore I must have Lagrangian as this. So this people have seen earlier like in some context. If there is, if the scalar field is real, then there is, this is usually half del mu phi minus half del square. Okay, so that's the case of normalization. So complex scalar field will do this, and real scalar field also will do the same equation. So that is scalar field mass. So therefore, if you want to look for what is the mass of a scalar field, you want to find that by looking at Lagrangian. What do? You look at the coefficient of phi square. That term is minus m square. So this is how we find mass of a scalar field. Look at the Lagrangian, look at a term which is phi squared, coefficient is given by minus m square. This will not come, it always works for normal scalar fields. Then there are gauge bosons. Gauge bosons are B or W. The determinism is A mu. Now for them, the kinetic term looks different, right? It's minus 1/4 f mu f mu. It's not the same as del mu phi star del mu. Although these are also bosons, the kinetic term looks like this. Now from this, you want to get this equation, right? Because the gauge boson should satisfy Kyle-Gordon equation. Okay, after all, bosons satisfy Kyle-Gordon equation. Turns out that if you want to get this equation, then you should add a term to this, which is half of m square times a mu a. I'll give it to you as a assignment now. So given this Lagrangian, which is minus 1/4 f mu plus half m square a mu a mu, you get this equation of motion by simply using this and keep track of indices well. That's all. So right now just take it from me. If you haven't worked it out before, at some point you should work it out and check for yourself. So note one thing, that this sign is different. It was minus m square, this was plus m square. Okay, but don't get worried. I think that I haven't made a sign. Okay, but you will check it when you actually do. Okay. So again, now if you have a gauge boson, and if you want to find out what is the mass of the gauge boson, you should look at a Lagrangian. Lagrangian, you should look at the coefficient of a mu or a square term. This coefficient is going to be plus half m square. That will give you the mass of this gauge boson. So that's how you find the mass of the gauge boson. If it's a Fermion, Lagrangian is this, and this Lagrangian will give you direct equation of motion, which is exactly what it is. Again, this is something that you have to do. So, how do you find the mass of a Fermion Lagrangian? Look for coefficient of psi bar psi. The coefficient is minus m. That's it. These are three rules of thumbs. For a scalar particle, coefficient of phi square is minus m square. For a gauge boson, coefficient of mu is plus half m square. And for a fermion, coefficient of psi bar psi is minus m, okay, not m square. Even dimensionally, the psi bar psi must have m in. So, when you want mass, you want terms like this. And the terms that we saw before, for example, these three, are not of that kind. I do not see anything that looks like psi bar psi times something. All these three are fields. There is nothing like m. M is a constant, no? Here nothing is a constant. So if I have 12 bar ur, this phi still exists. That's not a constant. Similarly, if I expanded form, it is yes. So here, for example, I have un bar phi plus er, not of the form en bar er. Okay. Here I have en bar phi 0 er, but this phi 0 is a field, so it's not a constant. It is not a mass. Something we noted the other day, and I just want to remind you that again, is that for a fermion, when I say psi bar psi, it actually means psi bar L psi r plus psi bar L psi. So this we saw the last time. You can't have psi bar psi L is 0 by definition. Usually you write this thing as only write psi bar psi r was condition. So now our job is to find out mass terms in Lagrange. How do you create mass terms? So this is when we come to, okay, so before we go to mass terms of fermions, this is gauge boson again. Again a repetition, but important to point out. We can't have a BU term because it will violate one. We cannot have a WU term because it will violate SU to it. We saw. What about fermion masses? You may have a term. I said, why don't you write a term which is NE times EN bar times ER? Will I be able to write this term down?
Why is not?
Why is not?
Not issue to tablet.
Y is of course not conserved. If you don't remember Y values, least thing you could check is that the EN is a doublet, SU2, ER is a singlet. Okay. You can never combine a speed half particle and speed 0 to get a singlet. That's another way of doing it. But both are perfectly fine. So in fact this term violates both SU2 as well as U2. So this is problematic. So therefore in standard model you cannot just go and write down mass terms for fermions like this. Similarly you can't go and write down mass terms for boson that looks like this. Because you violate on your PhD and you don't know to break the unit. So we found a way out of this, right? The way out of this was the Lagrangian will stay invariant under SU2U. Okay. But initial condition will not. So vacuum will not. So vacuum will break SU2 cross U. This is okay. This is fine. This does not create problems with our theory and its renormalization. Vacuum breaking is fine. What is problematic is gauge bosons. So this is how to break vacuum. That is Higgs mechanism.
Yeah, we got it.
So I repeat this. So how do you break vacuum? So for vacuum you use what's called as elliptic symmetry breaking mechanism. So let me remind you of what it is. So remember we had this potential V phi. So potential V phi came as minus V phi. Now this must have a m square phi square because m square stands for mass of Higgs. So there will be a minus, so V5 will be m square phi square plus something. So we postulate that this something is some lambda times phi dagger phi the whole square. You don't have much choice because I told you, you have to write down terms, say invariant under SU2 cross U1. And you are not allowed to have more than 4 dimensions. So therefore, if you want to write in terms of Higgs, only terms you can write are phi dagger phi and phi dagger phi squared. You can't go beyond. Okay, so this is the only one that we can. So let's write down phi in the most general term. So this is just 1 by root 2 normalization. This is phi 1 plus I phi 2, phi 3 plus I phi 4, because both are in the complex numbers. So now what happens is when mu square is less than 0, you get this Mexican hat kind of potential. And then the minimum is not at phi is equal to 0 but somewhere else. So this is your Mexican hat. So this is phi is equal to 0, not a minimum. The minimum is at some value. So if you want to find where the minimum is, this we did last time. Minimum happens to be at mu square is equal to 2 lambda times phi dagger phi. That corresponds to solution is says phi dagger phi is minus mu square by 2 lambda. So, minus mu square. And mu square is negative, so this is a positive quantity. So phi 1 square plus phi 2 square plus phi 3 square plus phi 4 square is constant given by mu square by 2 lambda. The potential is minimum over this whole surface. This is a 4-dimensional surface. So therefore, all the points on this surface are equivalent at this point, which is a symmetry. Symmetry says that there is no difference in all these points. Potential is the same at all these points. Now, I'll break the symmetry by hand.
Typically, it would be I have a infinite choice of vacuums.
Yes.
But since our vacuum is this, so wait, that is
Each point I choose will give a different vacuum. Right? Each choice of phi 1, phi 2, phi 3, phi 4 is correspond to a vacuum. One of these vacuums is our vacuum. So we will see what that vacuum is. We know certain properties of vacuum should have. Should have no charge, for example. Vacuum having electric charge will be problem. The electric charge seems to be the quantity which is conserved all around. So we choose a point. So I first tell you the choice, and then we see how the choice works. Okay. You can always try to take some other choice and see why the choice does not work. Okay. So maybe I will let you know the answer. So the choice that actually works is a very simple choice. Choice is phi 1, phi 2 and phi 4 are 0 and phi 3 is equal to V. That's the choice. What does this choice mean? This choice means, so I forgot to go by 2. This means that I only have phi 3. Phi 3 is a real quantity. This quantity I can write as V, which is the minimum point in vacuum, plus some field H, which is just your phi. So whatever I wrote as phi earlier, now I write as phi 1 is 0. See, phi had 4 degrees of freedom. Phi 1, phi 2, phi 3 is 0. It's a very big object. Although we did not write it explicitly, it was 4 real parameters: phi 1, phi 2, phi 3, phi 4. Now I say phi 1 is 0, phi 2 is 0, phi 3 is 0, phi 4 is 0, and phi 3 is V plus H. So what does this do? So in the vacuum, therefore, H is 0 and I have only V. So what is the T3 of V? Of this V? It's minus half. So phi vacuum is 0. This is what I call as phi 0. So this phi 0 has T3 is equal to minus half, because it's V is here, which means that in the vacuum I have a field which has T3 equal to minus half. This means that my T3 is not conserved in vacuum. Similarly, if I find the Y of this, Y of Higgs is plus 1. Therefore, Y is not conserved. However, it turns out that if I calculate T3 plus phi by 2, I take it, look at T3 of phi 0, Y of phi 0, I see that if I make a combination which is T3 plus phi by 2, that is equal to 0. This means that my vacuum still conserves this combination. This is a combination that we call as elliptic charge. So therefore, we have often seen this relation, right? Q is equal to T3 plus phi by 2. The reason this relation exists is because we know that Q is constant. In fact, now I can tell you that the way you find out the value of Y is in this fashion. Because you determine the value of Q, you know that this has to be satisfied. So you determine the value of Q, you know all Q's are, you have memorized all Q's, right? Minus 1, 2, 3, 0, blah, blah, blah. You know T3, it's very easy. Reaction net particle, half or minus half, and net particle 0. Therefore you know what is Y. So knowing this, you never have to memorize table of Y, because Q's and T3s are known to you. However, if we actually come through the standard model way, Q is a derived quantity. Normally we take Q as a known quantity, because that's what we learn throughout our classes. Okay. But in standard model, fundamental quantity is T3, another fundamental quantity is Y, and Q happens to be a combination of these two which remains constant.
Why not Q is equal to 2 times T3 plus Y?
That's okay. It's normalization. So definition of Q.
If you measure in terms of any one particle, you will still get the same. If I measure my mass, the charge of proton in terms of charge of electron, you will get minus 1 times. No matter what you write.
You're changing units, no? You're saying Q is equal to 2 times T3 plus Y. You're changing units. Which is fine. The electron charge will not be equal to minus 1. It will be minus 2. Proton charge will be plus 2. So all charges will get multiplied by 2. It's just like you're changing unit of charge. You can allow to do that. Okay, so this is fine, right? So this is how you break your electronics. The only thing you do is you are out of this 515 to 5354, 53 is equal to V. That's it. Now we'll see how to give masses to gauge bosons. So how does that happen? So relevant terms are this. These are the gauge modes of boson analytic terms, and these are the couplings of gauge bosons with Higgs. So write down this term. So this V5 is fine. So now we are at a minimum of this V5. Minimum of V5 means that Higgs is equal to 0 V. Minimum means that phi is equal to, so V5 minimum implies phi is equal to 0 V. Not that. That's all. So now we want to see what is this term when we replace phi by this 0V and see what it gives us. So let us do that. this is the term. Okay. W dot tau By times phi mod square. This is exactly what I had. Just saw that. Then, so this is, that's it. I replace phi by 0v. Then I can write down my w dot tau as, so w dot tau is no, w1 tau 1 plus w2 tau 2 plus w3 tau 3. So w1 tau 1, so this w1 comes here and here. w2 tau 2, so w2 comes here and here. I think perhaps I missed the sign. Yeah, so this should have been a minus sign. This should be a plus sign. So w2 comes here and here. w3 is here and here, minus w3 minus w3 multiplied by g. So that is a multiplication by g. Okay. And then there is g by 2, so that's 1/4. And phi is 0v by root 2. So that gives you 1 by. Normalization is fine. So my g therefore gives me something like this. My g prime is just diagonal thing. So it's y for phi is equal to 1. Y of phi is 1. So this is just g prime times b. So it's g prime b here, g prime. I omitted all the mu's for simplicity. Everything is just a mu's. So everyone agrees that this gives me this. Look at it for a few moments. There's no cheating now. Okay. So now what happens? Now, if I multiply this by 0v, that is, this will give me 0, and this will give me g times w1 minus iw2 times v mod square. So it gives me g mod w1 minus iw2 square times v square. This is what this term is. Then the second is this. So again, this will give me 0, and this will give me minus gw3 plus g prime b mod square. So plus minus g prime b plus gw3 mod square.
Squaring should be done after the solution.
So let me think. So this is vector, right? So let me write this thing down as, write one here. What? I will know multiplication. The upper part is this g w1 plus equals to, so g w1 minus iw2 times b. Lower part is, this will be 0, this part. So lower part is minus g prime b plus g prime b times. This is the vector. Then I do mod square. And then I don't know why I have to do this is like. Mod square is square of top plus square of bottom. So let's see what this is. This is I. So therefore this first term will become g b square is a 1h. So either 1/8 g b square times w1 square plus this again I. So mod I square is equal to 1. So 1/8 GB square W2 square plus 1/8 V square times mod of minus G prime B. So now we immediately see what has happened. Because of this, somehow we ended up getting a term that looks like W1 square, W1, which is the coefficient equal to 1/8 of GD square. Okay. Now 1/8 is a constant, G is a constant, D is a constant. So therefore this actually does look like, earlier we remember we said half M AU M squared. So this tells me that now I have a particle which I call as W1. W1 has a mass of, this is half M squared. So mass of W1 is equal to G squared. So now my W boson W1 has a mass equal to half G. Similarly, my W2 has a mass equal to half G. So two of my gauge bosons now have a mass. The mass came because V was non-zero. And V was non-zero because I chose this potential, which was minimum at. So this is how my W1 and W2 got a mass. So therefore, these two terms will give me mass for W1 and W2. Now let's look at the third term. Third term is 1/8 V square minus G prime V plus G W3. Now this term, let me write it down. 1/8 V square one way to look at this is if there was a gauge boson which was G prime V plus G W3, then it will have this mass of 1/8 V square. You agree with this? So to normalize, of course, we will normalize things there. So therefore, normalization for this would be minus G prime V plus GW3 divided by root of G square plus G prime square. And then this becomes G square plus this is normalization because it's G and G square. So now, if it turns out I can call this as some gauge boson, and I will actually call it Z. Then this term becomes Z square, 1/8 of V square, and G square plus G. And what does this tell me? My Z has a mass which is equal to 1/2 V square. Okay. Now that you form the combination Z, which is G prime minus G prime B plus G, there would be a leftover orthogonal combination. This is like cos theta sin theta. So what would be orthogonal combination? I will have G times D plus G prime times W. So what about this combination? So G times D plus G prime times W, and I will have each of this combination. This is left over part. Okay. However, I did not get this term. So I should actually get this square times something something, and this something I would normally call as half of square of this thing. But I did not get this one. I didn't get this term. And that means that my MA has to be equal to 0. This is a particle which is a combination of B and W. Okay. And normally we call this particle as a photon. So what has happened because of electric symmetry breaking, or electric mixing, this is mixing. We had W and we had B. But they were independent. So W1 and W2, for example, got masses separately by themselves. If you look at this term of this kind, this term has B square, W3 square, and W3B combination. So therefore, this W3 and B mix amongst each other. You can't have them separately. So if I write this, I will write this thing as, let's say, 1/8 of B square. Then I will have G prime with G and G prime are real. So G prime squared B square plus G squared W3 square plus twice G prime B W.
But also we get double plus and double minus. So that's a combination of double.
W1, W2. So let those be separate. Okay. So this is what we get. So then we can write them as a matrix. So W3 times G square plus B times G prime square, and these two are the cross terms. Minus 2 G prime. Here it minus 2 G prime minus. So actually W3 and B mix. And you know what happens when you get things that mix? Diagonalize. You find eigenvalues, you find eigenvalues. This should be a reflex action. Find at least two-by-two matrix which is observable elements. First thing you should do is find out mixing angle, find out eigenvalues. Okay. So we find eigenvalues of this. Okay. Can you tell me eigenvalues of this? One of them has to be 0. Why one of them has to be 0?
Because you know it earlier as you can also see. Because you expect the photon.
Okay, beautiful photon. Look at this matrix. Look at this matrix. What happens when the eigenvalue of the matrix is 0? 0. So one of this matrix is 0. So one of them should have eigenvalue equal to, one eigenvalue should be equal to 0. Now I tell you one is 0. What is the second?
G square plus G dash.
Yeah. That's because the trace is some of the super. So we did half the part. Okay. So eigenvalues are 0 and G square plus G prime square. Two-by-two matrices you shouldn't need to solve an equation. You just know these things. So therefore, I call these eigenvalues, this is 0, this is G prime and G prime. Okay. And I call these two as B and Z. Sorry, A and Z. Okay. What is the mixing angle?
But we have calculated the eigenvalues. Why not put G square plus G prime square first and then 0 then?
Yeah, that's okay.
Interchange
A and Z. Interchange A and Z. So it's my definition. See, right now there's no definition of A and Z, right? I haven't told you what the A is. I haven't told you what the Z is. Okay. So one with 0 eigenvalue I call as A, and one with other finite eigenvalue I call as Z. That's just my definition. Okay. Can you tell me angle? Can you tell me the mixing angle for this? Okay, we will do mixing angle. So we have seen before what happens when you have to mix. Right? Tan 2 theta is easier. What is tan 2 theta? Can you tan 2 theta and I will tell you what is it? So my tan 2 theta is 2gg prime divided by g square minus g prime. This actually happens to give you tan theta equal to g prime by g. So mixing angle was just simple g prime. I actually had given you the answer here because this I said, oh, this looks like sin theta, this looks like cosine theta. And I said g prime equals g w. So g prime by g was just equal to tan theta. This is called theta w because it's named after micro. It's not micro level. So W is the micro level. So clearly, what does this mean? This means that the mass of A is 0, the mass of Z is half V times square root of this. So this is what we have got. So we got two particles, W1, W2. Their masses were equal to half GV. And then we had Z, whose mass was half V times root of G square over G times. If you combine these two, then we get this ratio mw square by mz square cosine square theta w, and that's equal to 1. G by this is equal to cosine. So let's notice a few things here. Firstly, it tells you that mass of W and mass of Z are proportional to V. That is expected. If V is 0, we won't have any mass. Second thing is mass of Z has to be greater than mass of W. Very important. This was one very important test. And this was it's not trivial confusion, right? It's not just in terms of some parameters. See that you find Z, its mass will be more than that of. Third test is if you do this ratio, mw square by z square cos square theta w, you will get 1. So this is a very strong prediction. So it's of course 1 at 3 level. If you get corrections, it changes. Okay, that comes first. At least to 0th order, this ratio, which is called as rho, is equal to 1. That happens to be a very strong test of standard model. We got this ratio equal to 1 because we started by saying Higgs has y is equal to 1. So this all actually boils down to that. So Weinberg and Salam in their paper showed that if you start with y is equal to 1 Higgs, then you get this ratio is equal to 1. This ratio, rho, is equal to 1. If you take any other Higgs, if you say take Higgs with y is equal to 2 for example, y is equal to 0, you will not get this prediction. So everything in some sense has worked the other way around. Because you wanted to get this ratio is equal to 1, you had to start with Higgs with y is equal to 1. And then y is equal to 1 and a doublet. So rho is equal to 1 actually comes from phi. So y of phi equal to 1. So what does this mean? Phi of phi is equal to 1. So phi is a doublet. You have to have a rescue. A top particle, so this is top particle. So what is the charge of this particle? Is T3 plus y by 2. T3 was half plus y by 2 was half. That's 1. Bohr particle was minus half plus half is equal to 0. That is the reason that this particle was called as 5 plus impact. So in some sense, we started by calling it 5 plus and 5 0. Reason was that we knew that at the end we will get something else. So all these things are interconnected. So the way I told you is in some sense post facto thing. We knew what the answer would be, and I told you how to get the right answer. Okay. The process of getting to the answer was complicated. Okay. So this is how the gauge boson gate works. Okay. As Indra mentioned, I told you about mass of W1 and W2. W plus and W minus are just combinations of W and W. So they will also have mass equal. So now comes the last part. These were masses for gauge bosons. How do we give masses to fermions? What did we have? We had these terms. No? QL bar phi C UR, QL bar phi DR, and lambda and LL bar phi ER. Okay. And I just gave them some coefficients, which are numbers. So now let's see. Let's take this term, which is relevant. So lambda E times L bar L phi ER. So let's see what happens to this term. Lambda E LL bar plus UL bar EL bar. This we did earlier. 5 plus 5 0 times. What happens in vacuum? In vacuum, phi 0 is equal to V, 5 plus is equal to 0. So this is lambda E. So this is equal to lambda E, EL bar, ER. Now V is a number. So this now looks like lambda E times V, EL bar ER. So it's actually minus lambda E. So this gives me that the electron now has a mass given by lambda E times V. So coupling constant times vector expression. Okay. So same process that gave us masses to gauge bosons also gave masses to electron. Similarly, let's take minus lambda D. We say QL bar phi times dr. So this is minus lambda D, QL bar DL bar 0 V dr, and that gives me minus lambda D times B. So this gives mass to M. So in fact this is what I call as MD. Lambda D times B is M.
L particle and R particle are now, we can say that have equal mass.
Yeah. See, now we can say this.
Yeah.
I mean, earlier, so I'll come to this. Just, okay. Remind me if I don't come to it.
Okay.
So then I wanted to write lambda U. So remember this was 12 bar phi C of UR. So this was minus lambda U. 12 bar U bar. Now phi C was, remember, phi 0 star and phi minus. Right? So this is V. V is real. It's 0 times UR. So now this gives me minus lambda u times p times. So this term with the phi conjugate gives mass to u time. So this is called a thing. So now to your question. So yes, earlier before mass term, all the left-handed particles were separate. All right-handed particles were separate. There was no connection between them. So now our terms look like ME, for example, EL bar times. Okay. Therefore, we can call it either a mass of EL or a mass of ER. Or we can even say that we have a particle called P, which is EL plus ER. Then this is just ME times E bar E. Because I know that, so this is, because I know that E bar E is just this. E bar E is EL bar ER plus ER bar. So now it's true. Now I can say that EL and ER have the same mass.
That's why neutrino is not getting mass then.
There is no yeah. So unless you had R particle, you could not get a term. So yeah, you should have a term like U is R times U R. Okay. But UR doesn't exist, so this term doesn't exist. So formulas were straightforward. So if you break symmetry breaking, these are the three terms that we got of electric symmetry. So this lambda U times V, lambda D times V, and this becomes lambda A times V. Okay. And then all our particles U, E and E get Dirac masses. Okay. These are called Dirac masses. Dirac masses are those which have of the form L bar R. So that's it. No more to know. So what you are seeing here today is how we can do masses to particles in a natural manner. Okay. So we managed to do that. However, whatever we did was not able to do masses to neutrinos. So that we'll see tomorrow. So now it means that we have to go beyond the standard model to give masses to neutrinos. So we will see tomorrow how we can.